All right, back to business. That 0 looks exceptionally small, doesn't it? There we go. Okay, can y'all see it or no? Want me to kill the lights more? Yeah, if you want. I don't care. Doesn't bother me. I don't care if you fall asleep now. All right, well, let's first check the form of this limit. So you've got to know what order of operations here. Tangent of 0, right? Tangent of 0 is zero. It's 0. Okay, and then squared. So 0 squared 0. So we get 0 on top. And in the denominator, we have 0 times sine of 0. What's sine of 0? 0. So we get 0 on the bottom. So we have 0 over 0. So we need to do something. Now, this one is hopefully ringing a bell in your head that's making you think of the junk over junk going to 0 thing. Remember that? So I'm going to write this as tan theta over 1 times tan theta over 1 times 1 over theta times 1 over sine theta. So I've pulled everything apart. My two tans being multiplied, my theta and my sine theta on the bottom. The issue I have, the only problem I have is this division by 0. It's created by this, right? Yes? How can you resolve that? You can introduce a theta on top, right? Which would essentially make that a 1, but I have to do theta over theta. So why don't I do that on the side? I'm going to introduce a theta over theta. I'm going to slide this theta over here, and that will fix that one, won't it? But what have I done? What have you done? What have you done? Yeah, this right here, sliding over, is going to make this okay, but now I've got a problem. This is division by 0, and this is division by 0, isn't it? I've got like a double whammy here. So, what about tangent? What's tangent? Sine over cosine. And I have another one, don't I? So isn't this sine theta over 1 times 1 over cosine theta times sine theta over 1 times 1 over cosine theta times 1 over theta times theta over sine theta times 1 over theta. Yikes. So this tangent here became these two, right? This tangent here became these. 1 over theta is 1 over theta. Sine, theta over sine theta is this one, and then I was left with that theta right there. I'm just drawing those to make sure you understand where all those pieces came from. Are y'all good? I'm taking all those away because they're just getting in my way. Okay. Whoa. What now? Put this theta underneath this sine. Take this theta, put it underneath the other sine. If you do that, they're no longer a problem. The rest are okay. So let me write this down. Limit theta goes to 0. I'm going to have sine theta over theta times 1 over cosine theta times sine theta over theta. Do I write too fast in class? Sometimes? Okay. You'll have to let me know. Yeah. I got you. Okay, that's everything right there. All of those should be good. Sine theta over theta is going to go to 1 because theta goes to 0. The junk is identical, right? They both go to 0. That's going to go to 1. What's cosine of 0? 1. So that's going to go to 1 over 1, which is 1. Sine theta over theta, again, is going to go to 1. 1 over cosine theta is going to go to 1. Theta over sine theta is going to go to 1. There might have been an easier way to do this. I mean, as far as like the way you broke things up in the beginning, I went off of what was suggested, and there's nothing wrong with it. We've got an answer. Our answer is 5, right? No. 1 plus 1 plus 1 plus 1? No. The answer is 1. All right, next one. What are we on? C? C. Limit. X approaches -4 from the something side. Sine x over 4 plus x. This is a tricky problem. So the first thing I'm going to do is I'm going to plug in -4 and see what I get. What is sine of -4? Well, is it 0? No, because sine is only 0 at 0 and pi and 2 pi and 3 pi and 4 pi. And so sine is not 0 at -4. So I don't have to worry about that. Can I say that it's fixed? Okay. How about the denominator? It's going to 0, isn't it? So I have the possibility of infinity, negative infinity, or does not exist. But this is a one-sided limit, meaning that the most likely I'm going to get an answer. But, pardon me? Yeah, it's going to be one of those. But that brings a bigger issue into play here because that fixed one on top, I don't know its sign yet. I don't know what it is, going to be positive or negative. But let's talk about the 0 part of it. I have a number line. I put -4 on here. I'm approaching it from which side? Left. Someone give me a number that's a little bit bigger than -4, or to the left of -4. -4.1. When you plug that in, 4 plus -4.1, you get what? I'm sorry, I didn't hear anything. You get a -0.1, so it's a negative number, right? 4 take away 4.1, it's negative. So I know my bottom is headed towards, I should say it this way. I know I had fixed on top. I know I had a 0 on the bottom. I know now that the 0 is going to be a negative number. Can I answer the question yet? What about, well, do I have to test it the other way? I don't. Is this enough? Do you know what the top is? Is it positive or negative? You haven't figured that out. That's why I said this problem is tricky. I mean, you have the number line part of it, and all the problems that we've done, you were always able to determine what that top one was pretty easily, right? Like in class, I think there was one that was going to positive 48 or something like that. It was very simple to calculate that. Here, not so much. You're going to have to know what sine of -4 is. So you can either break out your calculator and make sure you're in radian mode, or you can look at the sine curve and think a little bit about what radians mean. Like pi is what? Approximately what number? 3.14, and 2 pi is twice that. So it's like 6.28, somewhere around there, approximately. So if I want to go and figure out what -4 is into the sine function, here's -3.14, right? Here's -6.28. You following what I'm doing here? -4 is back here. sign is what there? Positive. So I can tell that that's a positive fixed number up there. So you get positive over negative, which is negative infinity. Next, unless there's questions. Would a negative what? No, negative. Different signs, opposite signs, negative, same sign, positive. It's just like multiplication. Maybe. Could be. What's that? I didn't hear. Oh, yeah. You know what? Since you suggest that, oh. Wait, say again. What were you? Yes. Cosine's the same thing, except that, well, here's sine, right? Goes backwards same way. Cosine, the only difference is starts at 1, comes down, comes back up like this. And those happen at pi over 2, 3 pi over 2. Now, my graphs kind of suck, but good enough. I mean, that red one's this right here is supposed to be right in the middle, but I'm erasing it. I don't like that. All right, what's happening here? Another tricky one. What happens when you plug pi over 2 in up on top? It's pi over 4 because you're taking 1/2 times pi over 2. So the top is really this. I'll write it out. Since this is a review session, I'll take a little more time. This is 1/2 times pi over 2 over, the bottom is headed towards cosine of pi over 2. So this top one is pi over 4. You need to know what tangent of pi over 4 is. Any ideas? Without a calculator, anybody have any ideas? No. Where's pi over 4 on the unit circle? Where's pi over 4 on the unit circle? That's right, it's 1. So this is pi over 4, right? Tangent is the y coordinate divided by the x coordinate. Since they're the same y and x coordinates, the ratio is 1. You're looking, all right, this is root 2 over 2. This is root 2 over 2. By definition, if this is a unit circle, if this is theta, tangent of that angle, well, sorry, if that's 45 degrees, if that's pi over 4, tangent of 45 degrees, pi over 4 is equal to this ratio, the y coordinate divided by the x, which is 1. I'm not going to give you some crazy angle that's not on the unit circle, but I'll expect you to know the common angles on the unit circle, as I would expect anyone who got through pre-cal to know. That's part of, that's why they call them prereqs. Okay, so what's the top headed to? We haven't figured this out. It's 1 over cosine of pi over 2. Again, you could go to this. I love the unit circle. That's the way that I work with trig functions. Cosine of pi over 2, I go to the angle pi over 2, which is straight up. Cosine is the x coordinate. 0. So I've got 1 over 0. Fixed over 0. Fixed positive over 0 is what we have, right? So fixed positive over 0. I have 3 possible answers. Positive infinity, negative infinity, or does not exist. I'm thinking it's going to exist because it's a one-sided limit. I'm only approaching from the positive side of pi over 2. Questions? Keep going. We're going to do a number line, yes. On the number line, I'm going to put pi over 2. And I want to approach from the plus side, which is the right side. But what am I plugging in here? I mean, where am I plugging this in? Pi over 2, something a little bigger. I can't think right off the top of my head of, not bigger, to the right, it's going to be a little smaller or bigger. What? Where's 0? 0 is over here, right? So a little bit bigger than pi over 2. Where am I plugging this in, though? Where's the part that's causing the problem here? In the cosine, right? So I'm trying to figure out, if I plug in a number that's a little bit bigger than pi over 2 into cosine, I know it's headed towards 0, but is it positive or negative? Pardon me? 2 pi over 3, that would be close. I don't know if it'd be close enough. Now, so who asked about the cosine curve? Here you go. This is it right here. Because you're trying to plug this into cosine, right? So why don't I transpose a cosine curve right on top of this? Cosine starts out at 1, and then it starts dropping down. Where does it go through the x-axis here? At pi over 2. Then it comes down and starts doing this. Do I care anymore now? I've figured out what I need. The information I needed was if I was coming in on the right side of cosine towards pi over 2, I know I'm headed to 0, but I'm below the x-axis. So I know that it's negative. So I had a fixed positive number on top. It was headed towards 1 over something headed towards 0 through negative values, which is negative infinity. Any questions? Sean? No? You good? Okay. Oh, yeah. Oh. So if I would have been approaching it from the other side, right, if this was a minus instead, then the numerator wouldn't have changed. It still would have been headed towards 1. But the denominator would be headed towards 0 through positive numbers. So it would have been positive over positive, which would give you positive infinity. What if I did not put plus or minus? What if I just didn't put anything here? You would have to check it both ways, and you'd realize they're not the same answer, and so it wouldn't exist. All right, let me see what's next. Limit, this is E. X goes to infinity. Cos X, or cosine X. I hear people say cos, so I'm just throwing it out there for you. What about this? Where's it headed? Where's the top headed? It's bounded. Cosine functions are bounded. So you have a bounded function divided by something that's going to infinity, don't you? 0. That's it? That's right. Bounded over infinity, which heads to 0. So there's no work to be done, but you need to identify that it's bounded over infinity. That's what I'm looking for on the test, that you were able to recognize that. Okay, F. Limit x goes to infinity, square root of x minus cube root of x. What form of a limit do we have here? Infinity minus infinity. And we do not like that. So Thinking conjugate? Okay. Anything else? The main two techniques that we've had up to this point were factoring and conjugate. Those are the two things that we did. Factoring we did in class. Conjugate was the one that was asked, our first problem we did, number 25, right? This one I believe is going to go best if we factor. And the reason why is because the conjugate for this one is not clean. Look, let me show you. If you try this, okay, is that what you would have come in with the conjugate, top and bottom, same thing? Oh, I forgot the x. The problem you're going to have is this. What's root x times root x? Okay, the middle terms are going to cancel. What's that? That's not just x because it's cube root times cube root. Cube root times cube root does not go away. Why does square root times square root go away? Because that's the same as the square root squared, right? If I take cube root times cube root, then that's the same as cube root squared. Those don't go away, right? Because it's a cube root and being squared. Square root being squared, that does vanish out or does cancel out. So this is actually going to create all sorts of chaos. So we don't want that. How would you have known that? Well, you stay behind and you talk about the review. Right? That's what you do. All right, so this product, yeah, exactly. I'm going to write these as powers of x. I'm going to rewrite that as, we did one like this in class. X to the 1/2 minus x to the 1/3. That's what the square root means. That's what the cube root means. That's just rewriting radical notation into rational exponents. Then do you remember what I did here? Common denominator between those two fractions. So what's a common denominator? 6. So just rewrite, okay? We're not actually going to do anything other than rewrite the fractions with common denominator. So 6. I need to turn 1/2 into something over 6. Multiply top and bottom by 3. 3/6. Minus, okay, turn 1/3 into 2/6. And then now you should be able to factor something out. And which one did we factor out? The 2/6, the smaller one, right? X to the 2/6. I'm out of room. I need to go to the next page. Okay. Whoa. What happened there? Factoring out x to the 2/6, you're left with x to the 1/6 minus 1. And that I like because now I have infinity here, but this times infinity minus 1. That's the form I have now. And that's the same as infinity times infinity, which is infinity. So the answer is infinity. Yeah, infinity. We're getting there. Hey, number 9. That looks familiar. Or not 9, G, sorry. Part G, number 9. Part G. Didn't I do that? Was that the one I was asked about in class? Or did we just do that? It's not exactly the same? Looks like it, doesn't it? Oh, okay. I'm not going to do this one. because we did that in class. This one's conjugate. Yeah, this is like the one that was in the book. Yeah. Yes. Okay, this right here is x to a positive power, right? So if I take a number and I let it become infinite, it gets bigger and bigger and bigger. I raise it to a positive power, it's going to stay positive, it's going to still stay big. So that becomes infinite. This one is infinite. Take away 1 doesn't have any effect on infinity. But now you're multiplying instead of the original problem. In the original problem, what we were subtracting infinity. That you can't tell. But if you multiply infinities, you know for sure it's going to be infinite. So done earlier. Kinda, right? I kind of did one similar to it. Okay, so I'm not going to go through that. But it's a conjugate one, right? All right, last limit of the evaluate limit section of the test, which is, or the review, which is limit, uh-oh. That should be h goes to 0, not x goes to 0. X goes to 0. If x went to 0, there wouldn't be any problems. So what do we get there? If h goes to 0, what are you getting up top? Root 2x minus root 2x, so you get 0 on top, 0 on the bottom, and now we need algebra. So what do you want to try and bring in here? What would you like to try for this? The what? Conjugate. I like that idea. And I'm going straight to the conjugate because I did not have a complex fraction. So I did not have a fraction up on the top that I had to get a common denominator with first. So now this is equal to, oh wait, here's my conjugate, I forgot. What is the conjugate? Root 2x plus h plus root 2x, same on the bottom, root 2x plus h plus root 2x. Two x plus h, then what? Minus 2x. Don't need that 2x in parentheses, right? H root 2x plus h plus root 2x. Two x's are gone. You have an h on top. Cancels out with that h on the bottom. You're left with a 1 on top. Don't forget that 1, right? You wouldn't want to come all this way and all of a sudden not have a fraction anymore. So I should have pointed this out earlier, but the x is just kind of coming along for the ride, isn't it? I mean, it's a variable. Where we're headed with this class, all of our limits are going to have variables in them like this with x's. From here on out, it's pretty much going to be there. At least while we're doing limits. We'll get past that and not have to worry about it. What now? Let h go to 0. I'm out of room. No more limit. 1 over, it's root 2x plus root 2x. So it's 2 root 2x's. And that, you can't do anything to that. Oh, you could rationalize it, but I'm just going to leave it. Okay, sorry. I'm drifting over here. We did 4, right? No, we didn't do 4. We didn't do 4, right? Let's do 5. 5's faster. Let's just do 5 real quick. And I'll come back to 4. I need a little mental break. 5's not as bad. 5. So I give you a function, capital H of x is equal to sine of 1 over root 3 minus x. First thing is, where is h continuous? Where is h continuous? Hey, where'd it go? There it is. What's going on here? Oh. Okay, I'm not sure what's happening here. Trying to open something for you. Section on continuity. Trying to reiterate this whole idea of, the review is not just the review. In the notes, types of discontinuities, left and right continuity, continuity at interval. Here we go. Theorem. Functions which are continuous. All polynomial functions are continuous. All rational functions are continuous on their implied domains. All trig functions are continuous on their implied domains. All exponential functions are continuous on their implied domains. So, getting back to this and saying, where is this continuous? What we need to do is just look at anywhere we might have a domain problem in this composition of this function. So where would we have an issue? If this right here was 0, because then it would create division by 0, or if that 3 minus x was negative, because then we'd have a square root of a negative. Agreed? Other than that, it's back to this. Right here. If G is continuous at A, F is continuous at G of A, then we have that the composition is continuous. In other words, if you're going to take a function and plug it into another function, as long as each of the functions themselves are continuous, all of them composed together will be continuous. So taking that knowledge, I know the sine function is continuous everywhere. Sine curves look like little waves. 1 over something is continuous as long as the division is not by 0. The square root is continuous as long as this is not negative. So all that just to basically come up and say, we just need to check out, make sure that this is greater than 0, right? Just make sure that what's under here is not negative and not 0, which means check where it's positive. I'm just adding x to both sides. x must be less than 3, that's where it's continuous. Wherever it's defined is where it's continuous. It's basically the domain here, yes. Because it's the composition of continuous functions. Each one of those functions is very nice, except where they, aren't defined. So it's domain. If you wanted to, you could write it like this in an interval notation. Like x belongs to this, or you could say the set of x such that x is less than 3. I'll take any of this. This. I won't take that. Yeah, at least solve for x. All right. Math's ready for. We're going to finish this up. Y'all okay to finish this up? Part B. Part B is find 3 functions f, g, and h such that the composition gives you back capital H. So we did this in class. You start at the outer function and then work your way in, or you could start at the inner function and work your way out. But we need 3 functions, f, g, and h. And we need the outer one to be the f, then the next one inside is g, and then the one all the way in the middle or inside is h. Any ideas? Sine x is the last one. 1 over x, the inside. 3 minus x. Careful. Okay, so would this work? Would that work? Plug this into here. Plug all that into there. You'd have it. Or there was another way we could have done this. Leave this sine x. Have this 1 over root x. And have this one what? 3 minus x? That would have worked also. So there might be several, options here for you. Maybe like 2 or 3 options. Either one of those breakdowns would work. That's all we want for 5. Okay, let's go to 4. Sketch the function. Here we go. What is this function right here? Parabola? What's that plus 2 on the inside there going to do to it? Move it where? Which way? Left by 2. Okay, I'm going to start drawing. Remember, if the number's inside the parentheses, it's a left-right shift. If the number's outside the parentheses, it's an up-down shift. Wow. Okay. I guess I don't have a choice. Okay, so it's been moved to the, what do we say? Left 2. So I'm writing in pencil because I'm going to come back and erase this in a second. Just something like this. I'm just going to get a rough sketch of what's happening. Negative x minus 2 is a line. Y-intercept is negative 2. Slope is negative 1. So if I go to a y-axis, negative 2 is my slope. So down 2 to the right 1. Oh, no, slope is negative 1. Apologize. Down 1 to the right 1. And I'm going to have this line. I better do this in blue or something. Hey, it looks like the parabola and that guy come together right there. And then what does the square root of x plus 1 look like? Square root function looks like a parabola that got cut in half and laid on its side, right? And then you just move it up one. So it looks like this. That's what those three functions look like, kind of. Oh, I got to take a call real quick. Hello? I want to cruise. Okay, so I'm going to look now at breaking this up. I need the parabola when x is less than -2. -2 is over here. So I want this parabola just this left side of it, right? So let me draw this left side coming in here like this. I can erase the rest of it. And should I put a dot here, circle, open, closed? According to the parabola part of it, it should be open, right? Opened up. It might get filled in a minute, but let's just see. Now, the next time I'm this line, and that line is between x is -2 and 0. So that's just this little segment right here. And do I want to put dots at the ends or circles? What do we got here? At 0, put a dot. So at x is 0, which means we're down here, I'm going to put a solid dot there. But on the other side right here, it's open. So we're just going to have a hole in our graph, aren't we? Looks like. Get that yellow thing out of there. I'll leave it, but it was in here. It looked weird. Okay, so I forgot to cut off the other side of the line over there. I don't want that over there. And then the square root function starts at 0 and goes. What about at 0? It should be open, so I should have open here. It's a good thing it's open, right? Because if it was closed, I'd have a dot here and a dot here, and then it wouldn't be a function, would it? Okay, there it is. Any questions on the picture? All right, second thing is, where is f discontinuous and why? So give me the types of discontinuities. So where is it discontinuous? Discontinuous at x is what? -2. Why? What's going on there? You have a what? A hole. Which I said you could also say what? Removable discontinuity. And then anywhere else? X is 0. Why? You have a jump. I ask a little more. I ask what the limit as x approaches -2 is of the function. What is it? 0. We're approaching -2, right? -2 on the x-axis, or the x value is -2. As we come in from the left, it's headed to 0. Coming to the right, it's headed to 0. Doesn't matter because it's a limit, right? As long as from the left and right are the same, we're good. What's the limit as x approaches 0 of this function? D&E does not exist. Because as we approach 0 on the x-axis from the left, where are we headed? Where is it headed from the left? -2 from the right, +1. They are not the same from the left and right. Since they are not the same, it doesn't exist. All right, we've gone through the whole thing, right? Okay. Well, hour 40 minutes. Yep, it'll be the full class, so come fed, come rested, come confident. Yeah, you don't ever want to go into a test like you know, feeling like, I'm done, no way.